Hello, my name is Sarah, and today I'm going to talk to you about Lesson 11.7, Strategies for Solving Series, particularly in testing for convergence and divergence. This lesson is basically just reaffirming our knowledge of all these different tests that we can use. We don't really need a calculator for this section because it's pretty conceptual, and forgive me if I cough in the middle of this because I'm a little bit sick right now. Alrighty, let's get started. The first test we'll cover is the test for divergence. This should always be the first test that you try out because it's so straightforward and easy to use. If you look at the basic structure of a series, you can see that it's a summation of a certain expression, a sub n. If you take the limit as n goes to infinity of a sub n, and you get that it does not equal 0, then we know that the series is divergent. Make sure to note that if you do the test and you get that it does equal 0, then that doesn't necessarily prove convergence. If you get 0 over 0 or infinity over infinity, the test is indeterminate and you're going to have to use L'Hopital's rule or simplify it in some other way. This test is very useful if the top and bottom have the same power, because then you know for sure that it'll simplify to some constant. Next, let's look at the geometric series test. This test is super useful in looking at power series, which you'll need for further lessons and for sure in the AP test. You can only use the geometric series test if the series is in the form a times r to the n minus 1. If the absolute value of r is less than 1, the series is convergent. If the absolute value of r is greater than or equal to 1, then the series is divergent. The sum of the series will equal a over 1 minus r. I like to remember this test for convergence by thinking about how fractions work. If the absolute value of r is less than 1, then the fraction will be a finite large constant. If it equals 1, it's infinity, and if it's greater than 1, then it will be very small and infinite. A lot of people will make the mistake when simplifying of forgetting that the final summation has to be 1 minus r in the denominator, not a constant minus r. So don't be that guy. The next test is the p-series test. This one is also super useful. In problems where you're going to have to use more than one test, the p-series test is often the second or third test that you'll use, often with a simplified version of the original series. We can only use this test if the series has the form 1 over n to the p. P is some constant. If p is greater than 1, then the series is convergent. If p is less than or equal to 1, then the series is divergent. I remember this again by thinking about how fractions work. If p is less than or equal to 1, then the denominator will get really small, and the numerator will get infinitely large. If p is greater than 1, then the fraction is automatically restricted, and the summation has to be finite. In this example, it'd be restricted to around 1. This test is useful once a series is simplified, often in conjunction with other tests. Remember that you can only use this test if n is by itself. Next, let's look at telescoping series. This one is probably the most cumbersome out of the bunch, but it's one of the only ones that you can easily get a finite sum out of, so that's pretty cool. This test works best if you have a series of a ratio with a constant or a simple polynomial in the numerator and a polynomial in the denominator. Basically, the series will simplify to a fixed number of terms. We're going to use partial fraction decomposition to first simplify the expression. Then we'll write out the different fractions as a series, and finally we'll write out the terms until we can see that they start canceling. Here's a helpful hint. If you can factor out a constant, do it. It'll often make your simplifying much easier, and it'll be more convenient to find the sum. Next, we have the direct comparison test. Basically, in this test, we'll be comparing a sub n to a similar and simplified b sub n. First, we have to find out whether b sub n is less than or equal to a sub n. You can do this by literally just comparing them numerically, or you can graph the two. For our purposes, I graphed them because it's easier to see. Then we're going to see if b sub n converges or diverges as it goes to infinity. If b sub n is greater than a sub n and it converges, then a sub n will converge. This is because since b sub n is greater than a sub n and it converges, it's going to restrict a sub n's space and push it down, forcing it to converge instead of diverge. If b sub n is less than a sub n and it diverges, then a sub n will diverge. This is because b sub n is lesser, and when it diverges it will push up a sub n, forcing it to diverge. It's easiest to look at this graphically as you can see on the slide. The conditions I just described are the only conditions that this works for, so make sure to always graph or have a visual representation in your head so that you don't get confused. The direct comparison test works best for very complicated series, such as series involving natural logs or complicated square roots. Your b sub n should basically be a simplified version of the original a sub n, or it can be something that you know for sure is less than or greater than the original. For example, for 1 over natural log of n, you would compare it to the expression 1 over n, because you know for sure that 1 over n is less than the original and it diverges by p-series. For the second example, I would use the expression 2 over n squared because you know that it's greater than the original expression and it's convergent by p series, so therefore the original will be convergent as well. Next, let's take a look at the limit comparison test. This one's similar to the direct comparison test, except this time you don't have to know whether b sub n is less than or greater than a sub n. Woohoo! First of all, we have to find our b sub n. It should be very roughly a simplified version of a sub n. For example, if my a sub n is x squared over root 1 plus n, your b sub n should be the square root of n. Now we're going to take the limit as n goes to infinity of the ratio a sub n over b sub n. If we can get that the limit is greater than 0, then both a sub n and b sub n will be convergent or divergent. Basically, if b sub n is convergent, so is a sub n. If b sub n is divergent, then so is a sub n. Be careful though, if you get that the limit is less than or equal to 0, then the test is inconclusive and you're going to have to try something else. I'd suggest the direct comparison test in most cases. Alrighty, next up we have the integral comparison test. Basically, we're going to compare a series to its integral because they're both just summations. For this test, we have a few initial conditions. In order to compare a sub n to its integral, a sub n must be positive, decreasing, and continuous. Cool. So now we have to take the integral from 1 to infinity of a sub n, and if it's convergent or divergent, then so is the series a sub n. Be careful though, this would be an improper integral, so make sure to write it as the limit as b goes to infinity of the integral of a sub n from 1 to b. This test is pretty useful for any a sub n that is easily integrated, or anything with trigonometry. For example, if your a sub n is a constant over 1 plus n squared, you should immediately recognize that as the inverse tangent formula. Oftentimes in these problems, they'll ask you for an explanation. If you use the integral comparison test, make sure to say in your explanation that the initial conditions apply, and therefore the test is capable of being valid. Sometimes when integrating, you have to use the techniques of integration that we learned in last chapter, so be careful. Next, let's have a look at the alternating series test. This one will often be used as the first test in a series of tests in testing for convergence or divergence. If you see the general form of the series a sub n multiplied by -1 to some multiple of n, you know for sure that you have to use this test. Make sure to note the initial conditions for this one. The limit of a sub n as n goes to infinity must be 0, and a sub n must be continuous and decreasing. If that's all true, then the series is convergent. Now we have to test for absolute or conditional convergence. If the series a sub n is divergent, then the whole thing is conditionally convergent. I remember this by thinking about how if they both aren't the same, then of course it will be conditional. If the series a sub n is convergent, then the whole thing will be absolutely convergent. I remember this by thinking about how since they both match up, then the whole thing must be absolutely convergent. It's important to note that this test sadly can't test for divergence. Also make sure that if the question asks you what test you used, you must include in your explanation that the initial conditions hold true and whatever other tests you used to test for conditional versus absolute. This test is good for any series involving the form -1 to some multiple of n, and you'll most likely have to use another test when finding absolute or conditional convergence. Next up, we have the ratio test. Basically, in this one, we take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Sorry about that. If we get that the limit is less than 1, then the series is convergent. If we get that the limit is greater than 1, the series is divergent. If the series is equal to 1, then the test is inconclusive and you'll have to use another test. This test is basically pretty useful for expressions involving n factorial because n plus 1 factorial is the same as n factorial times n plus 1. So the ratio will simplify very nicely. Be careful though, don't forget that if the limit is equal to 1, the test is inconclusive. Also, later on when we do power series, we'll be using this test to find the interval of convergence. Awesome! Finally, we have the root test. Basically, we take the limit as n goes to infinity of the nth root of a sub n. If the limit is less than 1, then the series is convergent. If it's greater than 1, the series is divergent. If it equals 1, the test is inconclusive. This test is useful for expressions involving a sub n to any nth power. So basically, if n is in the exponent, you want to use this test. Remember that you can't distribute the nth root through addition. Also, if you end up with the limit as n goes to infinity of n over n to the 1 over n, that does not equal 1, as tempting as it sounds. You'd end up with infinity to the 0 power, and you'd have to use L'Hopital's rule to take the limit.